Hello, my dear friends. I welcome you all for this lecture. So, today we will discuss about the chapter number 6, Electromagnetic Induction. In this, we will discuss about the eddy currents or focal currents. So, the eddy currents means what? So, these are the currents induced in massive conductors when the magnetic flux linked with the coil or conductor changes. Okay, so the induced circulating or looping currents produced in a solid metal due to the change in magnetic field or the magnetic flux in the metal are known as eddy currents. So these eddy currents means, so if you take the metallic block, okay, in this metallic block, then the suppose the circulating or looping currents produced in the change of the magnetic flux due to the change of magnetic flux, then the metal are known as what? The eddy currents. What are the circulating currents what forming in this that are known as eddy currents. Eddy currents produces due to the change of magnetic flux. So these are also known as Foucault current. Foucault is the scientist name. So he observed that when a metal plate moved in a metallic field or the metal plate is placed in changing magnetic field, induced current produces in the metal, then such currents are known as eddy currents as they look like a circular, okay, and that are swirling eddies in water, okay, whatever the in surface of water, if you throw the anything, okay, any small piece, then whatever the circular waves are forms, like that same the circular waves are forming in it, and the eddy currents flow in circular paths and their direction is given by Lentz's law. Using Lentz's law, the direction is given, and the eddy currents are also known as Foucault currents. Okay, this is a observer, okay, scientist name or observer that finded the eddy current. Then the eddy currents are having some applications. So we'll see the applications of eddy currents. In induction furnace, eddy currents are used for metallic iron ore, etc. Okay, in induction furnace they are used. Then in speedometer, eddy currents are used to measure the instantaneous speed of the vehicle. Okay, so in this way, in speedometer also the eddy currents are used. In deadbeat galvanometer, eddy currents are used to stop the damping or the damping of the coil in a short interval. So, like this, the deadbeat galvanometer also the eddy currents are used. And in electric breakers of the train, the eddy currents are produced to stop the rotation of the axial of the well. And after that, they are used in energy meters or watt meters, and the eddy currents they are used to measure the consumption of electric energy. And in diathermy, eddy currents are used for localized heating of tissues in a human body. Like this, the eddy currents are having some applications. So, the eddy currents are used in induction furnace also. They are used in speedometer. They are used in deadbeat galvanometer. They are used in electric breakers. They are used in energy meter or watt meter, and they are used in diathermy. Like this, the eddy currents are having some applications. So after that, we'll see the eddy currents. After that, we'll see the self-induction. Okay, what is meant by the self-induction? So self-induction means what? The self-induction, you should see, it is the phenomenon of induction of EMF and hence current in a coil due to the variation of current in the same coil. Suppose you should see the one circuit, okay, so that is connected with one coil. After that, you should see the that is connected to rheostat and battery plug key. Suppose when the current increases in the coil, then the magnetic flux increases. If the magnetic flux increases, EMF is also increases. Hence, current induces in the same coil, and this EMF opposes the growth of the battery or current. When the current in the coil decreases, then the EMF decreases, the magnetic flux is also decreases. Hence, current in the induced coil, okay, and that is also decreases, and the current in the same coil, okay, this EMF opposes the decay of the current according to Lenz's law. Okay, so like this, the direction of induced current in the coil is because of the Lenz's law. Okay, it is opposes. So the self induction is what? The whatever the decay of current or the direction of induced current or the opposition of EMF of current is present in the same circuit. Okay, so that is known as self induction. So self induction is the phenomenon of inducing EMF in the self coil, okay, in the same coil due to the change in current and hence the change in magnetic flux in the coil. So this the self induction, the induced EMF opposes the growth or decay of current in the coil and hence delays the current to acquire the maximum value. Therefore, the self-induction is also known as inertia of electricity as it opposes the growth or decay of current. Okay, so self-induction means the whatever the opposing factor. Okay, so according to Lenz's law, suppose the current is increases in the coil, so the opposition is present in the itself, self induction. Okay, that is known as self induction. Growth or decay of current it always opposes. So therefore the self induction is also known as the inertia of electricity as it opposes the growth or decay of the current. After that, we'll see the self induction. So according to the self induction, the phi is directly proportional to I. Okay, in this self induction, the phi is what? Magnetic flux linked with the coil. Phi is what? The magnetic flux linked with the coil. The Magnetic flux linked with the coil is directly proportional to current flowing in it. So phi is directly proportional to I. So flux is directly proportional to current. If you will take the proportionality sign to equal sign, you should take phi is equal to L into I, where L is what? It is the constant of proportionality, and it is also known as the coefficient of self-induction or self-inductance. Okay, so the self-inductance or the coefficient of self-induction. Suppose the I is equal to 1. Okay, the current is unity, then the L is equal to phi. Thus, the self-inductance is also defined as, okay, the magnetic flux linked with the coil when unit current flowing through it. Okay, so that is what the self-inductance is defined as the magnetic flux linked with the coil when unit current flowing through it. So suppose the E is equal to minus d pi by dt. This is according to Faraday's law. The EMF is equal to the rate of change of magnetic flux linked with the coil. So that is the E is equal to minus d phi by dt. Therefore, the E is equal to, we will write minus L di by dt. Okay. So suppose it is minus L di by dt, where the E is equal to, that is, what is L? L is only the coefficient of self-induction, and that is a di by dt. So after that, if the di by dt is equal to 1, the rate of change of current is equal to 1, then L is equal to I. Okay, L is equal to E. Suppose the L is equal to E, it means the self-inductance is defined as the induced EMF set up in the coil through which the rate of change of current is unity. Self-inductance is defined as the induced EMF set up in the coil through which the rate of change of current is unity. So I repeat, the self-induction is the phenomenon of the inducing EMF in the self coil due to the change in current and hence the change in magnetic flux in the coil. Okay, so whatever the opposition forms whenever the current is increases in the coil, so in self coil only the opposition forms, that is known as self induction, and the induced EMF opposes the growth or decay of the current in the coil and hence the delays the current to acquire the maximum value. And the self-induction is also known as the inertia of electricity as it opposes the growth or decay of the current. So this is about the self-induction. So what is meant by the self-inductance? Self-inductance, so that is what? Suppose the magnetic flux linked with the coil phi is directly proportional to I. So I is the amount of current flowing through the coil. So flux is directly proportional to current. Then the proportionality sign to equal sign you should take. Phi is equal to L into I, where L is the proportionality constant, or it is also known as self-inductance, or it is also known as coefficient of self-induction. Whenever I is equal to 1, current is unity, L is equal to phi. Then the self-inductance is defined as the magnetic flux linked with the coil when unit current flowing through it. So Therefore, E is equal to minus d pi by dt. So, if E is equal to minus L di by dt, if the di by dt is 1 unit, then L is equal to E. So, the self-inductance is defined as the induced EMF set up in the coil through which the rate of change of current is unity. So, next we'll see the SI unit of self-inductance is Henry. Okay, and the self-inductance is said to be 1 Henry when 1 ampere current in a coil links the magnetic flux as a 1 Weber. Okay, so this is what the suppose the L is equal to 1 Henry. Okay, and after that the current di by dt, okay, current is a suppose 1 ampere. That time the self inductance is said to be 1 Henry when the 1 ampere current in a coil links the magnetic flux of 1 Weber. Or it is also defined as the self inductance is said to be 1 Henry when unit rate of change of current, okay, that is 1 ampere per second, because the di by dt is a 1 ampere per second induces EMF of 1 volt in the coil. So that is what the self inductance is said to be 1 Henry when the unit rate of change of current 1 ampere per second induces EMF of 1 volt in the coil. So this is about the self inductance. And the if they will ask write the self inductance of a coil, okay, so how to write the self inductance of a coil is the EMF induced in the coil due to the unit rate of change of current in the same coil. Okay, so self inductance of a coil is what? It is the EMF induced in the coil due to the unit rate of change of current in the same coil. So that is E is equal to minus L di by dt, where E is the EMF of the induced coil, EMF induced in the coil, and L is what? The self inductance, and the di by dt is the rate of change of current in the coil. Di by dt is what? The rate of change of current in the coil. So therefore, the self-inductance of a coil is the EMF induced in the coil due to the unit rate of change of current in the same coil. Okay, because of same coil, the name is self-inductance. So after that, we'll see the expression for self-inductance of a solenoid. Okay, so here this is a long solenoid. Okay, it is having the so many n number of turns of the coil. Okay, so solenoid is a long conductor and that is having the so many n number of turns. Let I, okay, I, L and N be the length, inductance and the number of turns respectively of the long solenoid. Okay, I is what? Suppose the here we'll take the L. Okay, L is the length of the coil, I is the current in the coil, and suppose capital L is the inductance of the coil, and capital N is the number of turns of the coil. Okay, suppose the number of turns of the coil, this coil, then the small n be the number of turns per unit length of the solenoid. Okay, so small n is what? Number of turn per unit length. Suppose it is having the 50 number of turns of coil and the length is suppose 2 meter, so that is 50 by 2. Okay, so like that the number of turns divided by unit length of the solenoid. Okay, so we should take the number of turns per unit length of the coil as a small n. Then experimentally the magnetic flux linkage is directly proportional to current in the solenoid. The flux leakage is n phi. Okay, so the flux leakage is what? Suppose it is n phi, that is directly proportional to current in the solenoid, that is I. Flux leakage, the n phi is directly proportional to I. Then if you should take the proportionality sign to equal sign, we should take one constant. So suppose L is the constant. So therefore n phi is equal to L into I. So because of this reason, okay, what is L in this equation? L is equal to n phi divided by I. Okay, so that is L is equal to n pi divided by I. The magnetic flux linked with the solenoid is phi, and the phi is equal to B into area of the cross section of the solenoid. Okay, so suppose that is B into A, phi is equal to B into A. Because of that equation, we will write phi is equal to B. B is a magnetic field, and into area of the cross section of the solenoid. Then the magnetic field due to the solenoid is equal to B is equal to, that is mu naught into Ni. Okay, so that is the B value is magnetic field. Okay, B value is equal to mu naught into Ni. Then after that the magnetic flux linked across the turns of the coil is phi per turns. Okay, that is phi per turns, that is B into E, where that is mu naught Ni into E. That is what? Mu naught Ni into E. So that is equal to, suppose the mu naught Ni into E. Suppose that is the mu naught Ni divided by L. Here, what is meant by small n? Small n is the number of turns per unit length of the solenoid, and capital N is what? The capital N is the total number of turns of the coil. Okay, so suppose if you will take equation in small n, the BA is equal to mu naught NIA, and if you will take the capital N, so that is mu naught NIA by L, because small n is equal to capital N divided by L. Okay, so after that the magnetic flux linked across n turns of the coil is, the phi is equal to mu naught n square Ia by L, but the phi is equal to L into I. So suppose the phi here, the L is equal to, okay, so in this equation phi is equal to mu naught n square Ia by L. In this equation we should take the phi is equal to L into I. So we will get mu naught n square A by L, that is equal to mu naught n square A into I. So this is the expression for the self-inductance of a solenoid. Okay, so this is expression for self-inductance. Suppose here the main thing you should see, the flux leakage is directly proportional to current in the solenoid. Suppose the n phi is directly proportional to I, then proportionality to equal sign n phi is equal to L into I, where L is equal to n phi divided by I, and according to the magnetic flux is equation, flux is equal to B into A, that is B into area of cross section of the solenoid, where B is what? The magnetic field due to the solenoid. So B is equal to mu naught Ni. The magnetic flux linked across the turns of the coil is phi per turn is equal to B into A. That is, suppose the mu naught Nia, and that is equal to mu naught Ni A by L, because the small n is equal to capital N divided by L, because the small n is what? That is the number of turns per unit length of the solenoid, and capital N is the total number of turns. And after that, the magnetic flux phi is equal to mu naught n square I by A, IA by L, mu naught n square IA by L, but the phi is equal to L into I, so the mu naught n square A by L, or that is equal to mu naught n square AI. So this is the expression for the self-inductance of the solenoid. Next, the energy in an inductor will take as a small work done, and we will solve. Suppose the dW is the small establishing the current I in the coil at small dt region, then dW is equal to minus EI into dt. So that expression to we'll see in next slide. Okay, so that is here I will tell about the inductor and that energy stored in the inductor. Okay, so first we will see what is meant by the inductor. It is the circuit element. Okay, inductor is the circuit element which opposes the change in the current flowing through it. It is the circuit element and that opposes the change in the current flowing through it. Suppose the energy stored in that inductor, that expression we'll see here. Suppose this is the here inductor. Suppose this is the inductor, and let dW be the work done. Suppose the dW is the small work done in a developing current I in the inductor as a time dt. Let E be the EMF induced in the inductor. E is what? EMF induced in the inductor. Then the small work done dW is establishing a current I. Then the coil at the coil of time dt, that is dW by dt is equal to minus EI. So therefore the dW is equal to dt, take this side, dW is to EI into dt, then dW is equal to L into I, that is di by dt into dt. Okay, because the E is equal to minus L di by dt, so because of minus, okay, it is plus, and the dW is equal to L into I into di, because the dt get cancelled. So therefore the total work done in establishing the current for I is equal to 0 to I is equal to capital I or I naught. So that is the W is equal to the integration of 0 to I naught Li dt. So that is equal to half Li square. By integrating this, you will get 1 by 2 Li square. So this is the work done in is stored in magnetic potential energy in the conductor, or it is energy stored in the coil. It is also known as energy stored in the coil, that is W is equal to 1 divided by 2 Li square. Okay, this is the expression for energy stored in a inductor. Okay, and what is meant by inductor? It is a element, circuit element, which is opposes the change in the current flowing through it. It is the circuit element that opposes the change in current flowing through it, and the energy in inductor is W is equal to 1 by 2 Li square. Okay, so here we'll see the W is equal to 1 by 2 Li square is the expression, that is the energy stored in the coil. Thank you.